All right, let's talk about trig functions. To begin with, consider a right triangle. Suppose the 90-degree angle is right there. And if we're talking about a particular angle, we'll call it theta, then you can define the sine as the ratio of the opposite side over the hypotenuse. The hypotenuse is the longest side. The opposite is the side opposite the angle theta, and the adjacent side is the side that is obviously adjacent or right next to the angle theta. So sine is defined to be the opposite over the hypotenuse. Cosine is adjacent over hypotenuse. And the tangent is opposite over adjacent. And note that tangent of theta is also equal to sine divided by cosine. Basically, what would happen is if you did sine over cosine, the hypotenuse part would cancel and you just get opposite over adjacent. So whichever one of these is more convenient, depending on the situation, is what you should use. They're both correct. We also have the reciprocal identities. We have 1 over sine, 1 over cosine, and 1 over tangent. Since those are needed for certain circumstances, we do have special names for them so that we can refer to them from time to time. The first one is 1 over sine, and it's called the cosecant. The second one is 1 over cosine, and it's called the cosecant. And the last one is 1 over tangent, and it is called the cotangent. So please take a moment to stop the video and take notes on these identities if you don't have them written down already. Otherwise, if you're ready, we're going to go on to the next slide. Just give myself a little bit of space here. I do want to talk about the unit circle. Now, if you have, again, a right triangle like this, the angle here with the 90-degree angle right there, and the angle theta that we're working with right here, that's the angle theta. Then, if you consider this particular triangle to be on the xy coordinate plane, centered at the origin, you get something that looks roughly like this. Now, notice that the adjacent side to the angle lies on the x-axis, and the opposite side from theta lies on the y-axis. Now, one last thing I want you to think about. Suppose we're talking about the hypotenuse having length 1 and it actually being the radius of a circle. We do call this a unit circle, where the radius is 1. Now, notice what happens here. The original adjacent side, the side that we would have called adjacent to the angle, is actually the same thing as the x-coordinate of the point right here. And the side that we would have called the opposite is actually the y-coordinate of this particular point right here. So what happens is it turns out that the adjacent side, the cosine of theta, is equal to the x-coordinate on the xy coordinate plane, and the sine of theta is equivalent to the y-coordinate on the xy coordinate plane. So if you have a circle of radius 1, in other words, if you're on the unit circle, cosine is your x-coordinate and sine is your y-coordinate. Just like that. Now, that is the beginnings of what I'm going to say about the unit circle. I'm also going to revisit it in a little while. But first, I do want to talk about some of the particular trig identities that we're going to need. So in order to do that, let's go on to the next slide and consider the Pythagorean identity. That's that sine squared cosine squared equals 1. Now, just to be clear about the notation, it can often be confusing for students, that sine squared notation. Note that the sine squared of theta, really all that means is sine of theta squared. It's really just a shorthand to put the square right there by the end. So remember, when you see that square, that it means that it's the whole thing squared. So the Pythagorean identity, that's that the sine squared plus the cosine squared equals 1, really comes back to that unit circle idea that I was talking about. If you have a right triangle, and again, suppose you're on the unit circle, hypotenuse is 1, remember that cosine is the x-coordinate and sine is the y-coordinate. Now, the Pythagorean theorem, remember, if this was side length A, and this was side length B, and this was side length C, remember the Pythagorean theorem tells us a squared plus b squared equals 1. Well, if you just translate this into our notation above, the x is the same thing as cosine, and the y is the same thing as sine. So really what you have here is sine squared plus cosine squared equals 1. So that first identity listed right here is a direct result of the Pythagorean theorem. And remember, it's a squared plus b squared equals c squared, but our c is 1 here, so 1 squared is just 1. Now there are a couple other identities that are very easily obtained from the original identity. The first one is if you consider sine squared theta plus cosine squared theta equals 1, that's just the original identity. Imagine dividing everything here by the cosine squared of theta. Well, what you get, remember, sine over cosine, remember, that's tangent. So just as a little reminder, tangent is sine over cosine. So that first fraction is actually just tangent squared. And remember, you can write the square right by the end, but right by the end, it's really a shorthand notation. Now, cosine squared over cosine squared, that's just the same thing over itself, which is 1, right? And 1 over cosine squared. Well, remember that that's secant, right? Secant of theta equals 1 over cosine. So 1 over cosine squared is obviously secant squared of theta. So what we've created here is just another identity that could be useful if you need to know something about tangent squared or secant squared. So go ahead and write down that new identity that we just created. I'm going to show you one more. So here we go. The second thing that you can do is take that original identity and instead of, last time remember we divided by cosine squared everywhere, this time let's see if we can divide by sine squared everywhere. Again, it's okay to do because you're doing it to both sides of the equation. Now sine squared over itself is of course just 1. Cosine over sine, well, remember that tangent of theta, as I wrote before, is sine over cosine. And then remember the reciprocal identity, cotangent of theta is 1 over tangent of theta. So if we have cosine over sine, that's just tangent flipped, which is going to be cotangent. And since it's squared, we're going to square it. Cotangent squared theta. And lastly, 1 over sine squared. Well, remember the reciprocal identity for sine was something called cosecant. So that would just be cosecant squared right here. And now, yet again, we've created another identity. This could be useful if you're doing some sort of calculation needing cotangent squared or cosecant squared. So we actually have created 3 identities here. And if you're ready, we can go on to the next slide. So go ahead and start reading this new problem. So if you've got the standard xy plane, an angle is said to be in standard position if it starts from the positive x-axis and then rotates that way. So we're talking about the point x is -2, y is -5. So that looks like this. 1, 2, and then 1, 2, 3, 4, 5. So the particular angle that they're talking about is going to rotate, just like I've shown, up until the point -2, -5, which is right here. So we imagine the radius starting here, rotating around until it stops at this point. So the angle theta actually looks like this. Now what we're going to do is I'm going to erase that rotation just for a moment, just to give us some space. And what we're going to do is we're going to imagine what would happen if we built a triangle right here. Well, obviously the right angle is right here, and we're going to consider this angle right here as a reference angle. Now think about what the side lengths look like. This side length right here has a value of 2, right? It's -2 on the x-axis, but the length itself is 2. And the length here on this side is 1, 2, 3, 4, 5. So basically what we have is a right triangle with side lengths 2 and 5. If we're going to find the 6 trigonometric functions of theta, we do need to have the hypotenuse as well. So here, if I just extrapolate that triangle for a moment, if you think about it this way, this is our angle theta right here. We got a side length of 2 and a side length of 5, and what we're really missing here is the hypotenuse, right? So a squared plus b squared equals c squared. That's 2 squared plus 5 squared equals c squared. Well, that's 4 plus 25. So c is going to be the square root of 29. So over here, this longer side, the hypotenuse, is square root of 29. Now that we've got all 3 sides, we should be able to fairly easily calculate the 6 trigonometric values. So here we go. We got sine theta, cosine theta, and tangent of theta. Remember that sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So for sine, it's and remember this is the reference angle right here. So opposite over hypotenuse, the opposite angle from here is 5, or the opposite side is 5. So what we've got here is 5 over the square root of 29. For the cosine, remember it's adjacent. The adjacent angle that's not the hypotenuse, the adjacent side that's not the hypotenuse side is 2. 2 over, again, hypotenuse square root of 29. And for the tangent, we do opposite, which is 5, over adjacent, which is 2. So we just get 5 halves there. Now, of course, at this point, we technically have calculated sine, cosine, and tangent. A lot of times people will prefer to see a denominator rationalized. That means get the square root out of the denominator. And you'd multiply by square root of 29 over square root of 29 to get 5 square root of 29 over a square root times a square root is just a number by itself. Similarly, cosine, you could rationalize the denominator. You'd get 2 root 29 over 29. So then these are the three answers. This is sine, cosine, and tangent. Now we were also asked for the other three, and so I'm going to need to erase and continue from there. So stop the video if you still need to take notes on this. Otherwise, we're going to go on. So here we go. So remember, on top of sine, cosine, and tangent, we also need cosecant, secant, and cotangent. Now remember, cosecant, that's the one that's 1 over sine. Secant is 1 over cosine. And cotangent is 1 over tangent. And remember that the sine, before we rationalize the denominator, was 5 over 29. 5 over square root of 29. So the cosecant would be square root of 29 over 5. The secant would be square root of 29 over 2. And remember that the tangent was 5 over 2, so the cotangent, the reciprocal of that, would be 2 over 5. So those are the values for cosecant, secant, and cotangent. But we've left something out. You may have noticed this. Recall that our original picture was that the original angle was supposed to be in standard position. Now all the trig functions that we found were technically just for this angle, but remember they wanted us to do the whole angle from standard position. So because of that, we also have to consider the sine, as in the plus or minus part of the values. So in this case, sine of theta, cosine of theta, and tangent of theta may or may not be negative. Well, remember that a point in quadrant 3 is going to have a negative x value and a negative y value, right? Remember that cosine corresponds with the x coordinate and sine corresponds with the y coordinate. So both cosine and sine are going to be negative. Now tangent, since tangent is sine over cosine, it's a negative over a negative, so it's going to become positive. So the sine of theta, remember the answer we got was 5 square root of 29 over 29, but it's actually going to be negative. Same thing for cosine. However, tangent is going to have a positive value because it's a negative over a negative, essentially. Cosecant of theta is going to look like a negative as well because all it is the reciprocal of sine. Ooh. Make that a little bit neater here. And secant is just 1 over cosine, so it's still going to be negative. And lastly, tangent. Remember, our tangent is positive, so if you do 1 over that, it's still going to be positive. So these are actually not for the reference angle, but the actual original angle in standard position. It's going to have these particular trigonometric values. Okie dokie, so moving on. If you were to consider the unit circle, remember again, unit circle is a circle of radius 1. So just drawing the best circle I can there. Use your imagination. Okay, so there are some common angles that people are interested in that we're going to memorize the cosine and sine for. And these can be worked out to a similar fashion as the last example. 30 degrees, 45 degrees, and 60 degrees. But in general, we're not going to measure in degrees. We're mostly going to use radians. So the first angle is pi over 6. So pi over 6. Second angle is pi over 4, and third angle is pi over 3. We also have the angle 0, right? And the angle pi over 2. Now we're going to talk about the actual coordinates of those points. Well, the first point has the coordinates square root of 3 over 2, comma 1/2. Second point has the coordinates square root of 2 over 2, comma square root of 2 over 2. And the third one has the coordinates 1/2, comma square root of 3 over 2. Now obviously this point right here is the point x is 1, y is 0. And this one right here is the point x is 0, y is 1, so that'll be 0, comma 1. Now remember that the way it goes, cosine is the x coordinate and sine is the y coordinate. That goes in alphabetical order, C before S, so it kind of makes it easy to remember if you think about it that way. So then just whichever angle you're talking about, you can just get it straight from the unit circle. So for example, if you were looking for, say, cosine of pi over 6, you're looking for the x coordinate of the pi over 6 angle, so the answer is just square root of 3 over 2. You do want to memorize the unit circle. One strategy that you can do is to memorize, in particular, the first quadrant, quadrant 1. And then just use the idea of whether or not it's going to be positive or negative to fill in the rest of the chart. So for example, in quadrant 1, So for example, in quadrant 1, the x values are positive and so are the y values. In quadrant 2, anything over here, the x value would be negative and the y value would be positive, because that's how something falls in quadrant 2. For quadrant 3, x values are negative and so are y values, kind of like that -2, -5 point example that we did at the beginning of the video. Also quadrant 4. And this one, the x values are positive, right? Because you're over here positive and y values are negative. Alright, so we'll just refer back to this as needed. If you do have a copy of the unit circle on hand, it's best if you get that out and look at it as we're going through the next examples. Which we'll do right now. So again, if you'll recall the unit circle, remember the first one was square root of 3 over 2, comma 1/2. Second point, square root of 2 over 2, comma square root of 2 over 2. And the last one, 1/2, comma square root of 3 over 2. Remember that the first angle was your pi over 6 angle. Second one was pi over 4, that's a 45-degree one. And the 60-degree angle is the same thing as pi over 6 in radians. So if you're looking for sine of pi over 6, remember that pi over 6 is this angle right here, right? And remember that the x-coordinate is cosine and the y-coordinate is sine. So for pi over 6, the sine is going to be just the value 1/2. Number 2 is the same problem, so let me change it to something else so that you get a different example. Let's do cosine. So let's suppose we were actually change that problem. Let's suppose we were asked to find cosine of pi over 6. Well, cosine of pi over 6 is the x-coordinate, so this becomes square root of 3 over 2. Now for tangent, remember that tangent is equal to sine over cosine. So for pi over 4, again, we're on this one. This is the cosine, this is the sine. So the sine is square root of 2 over 2. That's the sine part. And the cosine is square root of 2 over 2 as well, which means that the tangent of the angle pi over 4 is just the number 1. Okay, so really quickly before we go to the next example, let me explain what a reference angle is. So if you have an angle other than the angles in quadrant 1, let's say for example 5 pi over 6. Well, remember that halfway across the circle is pi. So if you're at 5 pi over 6, you're 1/6 of a pi short of being to pi. So again, we know that halfway across the circle, I'll just write this really quickly, you already know this, but halfway across the circle is the angle pi, right? Here we're on 5/6 pi, so we're 5/6 of the way there. That means that this angle right here is actually pi over 6. Pi over 6 is called a reference angle. So basically what a reference angle is it's the angle that would be the closest angle made with the x-axis. So let's do some examples finding the trig functions of any angle outside of quadrant 1. Reference angles are probably the easiest way to do this. So let's get going. So we're finding these exact values, and we are asked to use reference angles to try and do this. And the idea is to try to use your knowledge of quadrant 1 to proceed. So the first angle there on that list of problems to do is 5 pi over 6. So that is actually the same angle we were just working with a minute ago. So remember, an angle is in standard position if it starts on the positive x-axis and then rotates from there. So this is 5 pi over 6 right here. Now remember that we were considering that to have a reference angle of pi over 6. Now remember that if you're at pi over 6, and I'll draw this off to the side, although it's best if you look at your own unit circle on your paper. If you're at pi over 6, remember that the point here was square root of 3 over 2, comma, 1/2. Now since 5 pi over 6 falls in quadrant 2 actually, what it means is that the x value is negative and the y value is positive. So this particular angle 5 pi over 6 is going to have the same point as pi over 6, except that the x value is negative. So this particular point right here is actually negative square root of 3 over 2, this point right here, comma, 1/2. And remember that cosine is the x and sine is the y. So, what's the value of cosine of 5 pi over 6? Well, it's going to be negative square root of 3 over 2. So that's how you can use reference angles to help you find a trig function. Now let's try the next one. Give me a minute to erase. Now remember that 1 pi is a half rotation. Here we're doing 3/4. 3/4 is not all the way to 1. So what we've really got here is 3/4 of the way to pi. So the angle 3 pi over 4 looks like this. Now if you consider the angle that would have been made if you went straight down to the x-axis, 3 pi over 4, we only needed another 1/4 to get to pi, so this is really pi over 4. So the reference angle for 3 pi over 4 is pi over 4. Now recall that pi over 4, that was the 45-degree angle. Coordinates of it, if you'll recall, are square root of 2 over 2, comma, square root of 2 over 2. So this particular point is going to have those same coordinates, square root of 2 over 2, comma, square root of 2 over 2, except that the x is going to be negative. The y is positive because we are on the positive y-axis part. Now, if we're looking for tangent, remember you got to do sine over cosine, right? Well, the sine, square root of 2 over 2, and the cosine, negative square root of 2 over 2. So this turns out to just be -1. So the tangent of 3 pi over 4, the answer is -1. Now for sine of 5 pi over 3, let's think about what's going to happen here. Well, five pi over 3 is almost 2 pi, right? Remember that a complete rotation is 2 pi. If that had been 6 pi over 3, it would have been a complete rotation. So when we rotated for 5 pi over 3, what happens is we rotated and we almost made it back to 2 pi. We were just shy of it. Like that. This is the angle of 5 pi over 3. Now if we got to 6 pi over 3, we would have done a complete 2 pi rotation. So this reference angle, the angle that would take us straight to the x-axis, is just 1/3 pi, right? Or pi over 3. Again, we just needed another third in order to make the complete rotation. So our reference angle is pi over 3. Now remember, pi over 3, that's the 60-degree one. The x-coordinate was 1/2, and the y-coordinate was square root of 3 over 2. This one is going to have the same coordinates, except possibly minus signs. Now, since we're in quadrant 1, 2, 3, 4 here, any point in quadrant 4 is going to have a positive x value and a negative y value. So this particular point is going to have a negative on the square root of 3 over 2. X value stays positive. Now, last thing, remember cosines first, sine second. So if we're looking for sine of 5 pi over 3, the answer is negative square root of 3 over 2. All right. What happens on this one if you think about 8 pi over 3? Well, remember that 2 pi is a complete rotation of the circle, right? Well, 8 pi over 3 is more than 2 pi, right? Because if you had a denominator of 3, 2 pi would be 6 pi over 3. So this is bigger than a complete rotation. Basically what's happening here is that we do a full rotation, a full 2 pi rotation, and then we actually keep going from there. So in order to get the trig value, we need the sine and cosine. We just need to find the landing spot of this thing. In this situation, the number of rotations doesn't matter. We just need to get rid of one or more of the rotations. So we really just need to take away a rotation. And we need a common denominator for that. So 2 pi is the same thing as 6 pi over 3. So this is really 2 pi over 3. Now 2 pi over 3 is 2/3 of the way to pi. So the reference angle is actually pi over 3 here, right? Because you need another 1/3 to get to the pi. Now with a pi over 3, remember that the x-coordinate is 1/2. The y-coordinate is square root of 3 over 2. And remember that x, when you're in quadrant 2, x is negative and y is positive. So it looks like this. So if we're asked for cosine of 8 pi over 3, remember cosine is the x-coordinate. So this is just equal to negative 1/2. Now let's think about 15 pi over 4. Now with a denominator of 4, a complete rotation is 8 pi over 4, right? Since 15 is larger than 8, it looks like we did an extra rotation here. Well, so what we can do is try to get rid of that extra rotation. This is 15 pi over 4 minus, if you got a denominator of 4, again, it's 8 pi. So keep the common denominator common. 15 minus 8 is 7. So this is 7 pi over 4. 7 pi over 4, notice, is just 1/4 short of being a full 2 pi rotation. So that angle should be, if you're coming from standard position, should be right here. So it is 7 pi over 4. And since we're just 1/4 shy of making it to the x-axis, our reference angle should be pi over 4, right? Which means that the point should look like square root of 2 over 2, comma, square root of 2 over 2. X-coordinates are positive in quadrant 4, but the y-coordinate should be negative, so the negative goes right there. And if you're looking for tangent, remember for tangent you got to do sine over cosine, which in this case is going to be the sine is negative pi over 2, negative square root of 2 over 2, and the cosine is square root of 2 over 2. So this actually turns out to be a -1. And then lastly, we were trying to find tangent of negative 13 pi over 6. Well, what's a negative angle? Well, a negative angle, remember that an angle in standard position rotates this way off the x-axis. But if you've got a negative angle, it's actually going to rotate the other way. So if your angle is negative, it's actually going to start here on the positive x-axis, But it's not, instead of standard position, it's going to go the opposite way. So we are going to rotate this direction. But we need to figure out where we're stopping. Notice how 13 pi over 6 is more than a rotation, right? Because again, a rotation is 2 pi. If you have a denominator of 6, that's 12 pi over 6. We're more than that, so we know that we've done more than one rotation. It's just going in the opposite direction. So here what you can do is you can actually add 2 pi to get rid of the rotation, because instead of taking it away, you want to add it since we're going the wrong way. So what you're really adding here is 12 pi over 6. And so you've got a negative pi over 6. You could add another 2 pi if you wanted to make this be a positive angle. That would be fine. Or since since negative pi over 6 is easy to interpret, you could just go straight from there. Either one is fine. So I'm just going to go ahead and view this as the negative pi over 6, and that's going to give me a reference angle of pi over 6. Alternatively, you could add 2 pi and make this 11 pi over 6. Same thing. Same landing spot, I should say. They're coterminal angles. So, if our reference angle is pi over 6, remember that's the one that has square root of 3 over 2 first and 1/2 second. Remember, y values are negative in quadrant 4. We got cosine first, sine second. So for tangent, if you're doing sine over cosine, then you've got negative 1/2 over square root of 3 over 2. And then if you just flip and multiply the denominator, you get negative 1 over square root of 3. And most people, that's the answer, but most people would like to see no square root in the denominator. Remember how to get a square root out of the denominator? You rationalize the denominator. Multiply by square root of 3 over square root of 3. What that does is it makes the square root be in the numerator, and square root times the square root is just that number right back. So this is a simplified exact answer for a tangent of negative 13 pi over 6 using a reference angle of pi over 6. Okay, so that's it for today. Remember to rewatch the video and keep notes on this. Thank you.